Welcome to particle physics. Let's talk about the Standard Model. The Standard Model does for particle physics what the establishment of protons, neutrons and electrons did for understanding of the periodic table and the source of what the elements are made of. The Standard Model gives us smaller subatomic particles that explain all the particles that we've encountered, both in cosmic rays and in particle accelerator collisions over the years. Well, the proton and neutron are two fairly recognizable particles that you should be aware of by the time you're studying particle physics. Protons and neutrons occur in the nucleus of atoms, and they go with electrons to form everything that we are familiar with in the periodic table. So all the elements are formed by different combinations of protons and neutrons, with equal numbers of electrons to the number of protons orbiting an atom. So about 100 years ago we thought we had established the fundamental particles that made everything up. And then collision experiments start to reveal other things. Cosmic ray events happening in the upper atmosphere were showing new particles forming, and scientists were sending balloons with experimental apparatus up into the atmosphere to find out about those things. We started getting all these other particles then detected that don't occur normally in nature, and we realized then that there was a lot more to this picture. Physicists built accelerators and smashed protons and electrons and things like that off each other to see what happened. And in the scattering experiments that they got, they started to realize that there were smaller particles within the proton and the neutron, and they were given the name quarks. So the idea of two smaller particles called the up and down quark was generated, and the up quark was thought to have a charge of plus 2/3 of that of a proton, and the down quark negative 1/3. So if you establish the idea then that these exist, then if you put two ups and one down together, you can generate a +1 charge, and that's your proton. If you put a single up and two downs together, you get a neutral particle that has no charge, and that is the construction then of the neutron. What then happened is that later experiments, theory suggested that there would be more, and the experiments revealed eventually the discovery then of the strange quark, the charm quark, the bottom quark, and the top quark. And these have all been found experimentally in collision experiments. So the quarks either come with a plus 2/3 charge or a negative 1/3 charge. And the extra ones had to be invented to explain various other kinds of particles and interactions that were occurring. But we can basically then construct lots of particles then from these, and that explained, for example, why we had seen so many particles, and it was originally called the particle zoo, that there were so many particles being discovered, and people worried about, how would this have an underlying simple explanation. And if you imagine that these quarks can have all these charges, and then if these go with their anti-quarks, the antiparticles of all of these, that gives you a total of 12 quarks with reverse charges, which allows you to make up lots and lots of different particles that would explain the overall picture that was emerging. We can take the up and the down quark in a combination of 3 to create a proton. If we have up and down and another up here, we create something that has a charge of +1. And to construct the neutron, again we take an up and a down, and this time we pick another down for the top position, we create something that has zero charge, in other words a neutral particle. So the proton is then UUD, and the neutron will then be DDU. So you can see that both the proton and the neutron contain an up and a down quark. It's the choice of what the third quark is that determines the difference between these two particles. So if you imagine that both of them in the bottom here of their little triangles have an up and a down, it's that top choice that swaps this particle from a proton to a neutron. You can see then that it must be the changing of one of these that's happening in beta decay, because in beta decay we either have a proton converting to a neutron or a neutron converting to a proton as part of the interaction. So it's this third quark and what happens to it that's really changing in beta decay. The Standard Model also predicts the idea that there are 6 other particles called leptons. Now there's one that we're familiar with. You will have come across the electron. And the electron has associated with it a tiny particle called an electron neutrino. But it goes further than that. The electron has a heavier cousin that's negative just like itself, called the mu. And the mu has associated with it a neutrino called the mu neutrino. And then it goes even further and we have a heavier cousin again called the tau, which is still negative like the electron, and it has a tau neutrino associated with it. Neutrinos are chargeless and virtually massless. We're not sure if they're totally massless or not. Particles, so they're very hard to detect, they're very weakly interacting. But the electron, the mu and the tau are all negative, so they're like heavier versions of each other. And those are all the 6 leptons. The leptons can all have antiparticles, and so the anti-electron is called the positron. There's an anti-mu and there's an anti-tau, and all the neutrino particles can have antiparticles as well. So we have 6 quarks, 6 leptons, and all of those can have antiparticles. And that's basically the particles of the Standard Model. So how do the forces of nature then operate in this system? Well, let's deal with the quarks first. Their behaviour is governed by the strong interaction or strong force, and its carrier particle is called the gluon. The job of the strong force is to bind everything together in nuclei, so holding the protons and neutrons together and then holding the nucleus itself together. That's what the strong force does. It kicks in at the tiny distances involved, and it doesn't really appear outside of that realm. Really, what's going on is that the transfer of this particle from one object to another is providing a force. And all of these force carrier particles, it's the exchange of them that provides the force. So exchange of gluons is what's providing the strong force. If we bring in the rest of the particles, we can include the weak force then, because it operates on all of them. And the weak force is carried by the W and Z bosons. We're obliged to say Z, even though I would say Z. So the W and the Z bosons, transfer of those, exchange of those between objects, is providing the weak force. The weak force is behind things like beta decay that we're familiar with. Now we haven't included electromagnetism, and electromagnetism will act on these charged particles. It won't act on these uncharged particles, and it will also act on the quarks here, which are also charged. So the group of charged particles will experience the electromagnetic force. So the force carrier for electromagnetism is the photon. So any attraction or repulsion between charged particles is governed by the electromagnetic force and the exchange of photons between the objects. Any strong interaction is governed by the gluon and its exchange. Weak interactions are governed by the W and Z bosons. So what do we get to find out about this? Well, the obvious thing to pick out is that leptons don't feel the strong force because they're excluded from its rectangle. All charged particles feel electromagnetism. Uncharged particles don't. So it's understanding the groupings of these and the exchange particles that make them happen that gives you an idea of how the force carriers all work. So where is gravity in all this, I hear you ask? Well, gravity, there's a theorized particle called the graviton, which supposedly will transmit the gravitational force. But the gravitational force is so weak that it can't easily be investigated in particle accelerators. And the graviton has never really been observed, so gravity technically isn't really part of the standard model at the moment until we understand it a little bit better. So this is it. We have our 4 force carriers, we have 12 particles, and that is the standard model. Next time we'll look at baryons and mesons. Thanks for watching.